Yes, can do that. Thank you. Often when we think about mineral nutrient dynamics in agricultural systems, we think about soils and fertilizers. I want to spend a few minutes today talking about the concentrations of mineral nutrients in the actual plant biomass in pastures and the relationship between those concentrations and the requirements of grazing livestock. Mineral nutrient management is essential. Proper dietary concentrations are required for livestock productivity and health. Surpluses can degrade the environment, and unnecessary additions can lead to economic losses. In terms of mineral supplementation in pasture-based livestock systems, many producers provide a consistent level of mineral supplementation. Be that a granular supplement or a block, these tend to contain calcium and magnesium, phosphorus, salt, and micronutrients at the cost of about $10 to $20 per animal per year. With a consistent level of mineral supplementation going on throughout the entire growing season that's often free choice. It's been shown that pasture herbage mineral concentrations vary throughout the growing season, thinking about the maturity level of forage and nitrogen and phosphorus and potassium concentrations falling from spring to summer as the forage mature. So with a consistent level of mineral supplementation but a varying level of mineral nutrient concentration in the pasture herbage, there's some opportunity for optimization there. And so a better understanding of the seasonal variation of herbage nutrient concentrations can lead to improved management. And so the objectives of this study were to analyze the seasonal variation in pasture herbage mineral concentration in tall fescue-based pasture with regard to beef cow mineral requirements, and to develop a statistical model to predict a variation in herbage mineral concentration throughout the growing season. And to do this, I had the opportunity to work with an existing data set from the Economic Pasture-Based Beef Systems in Appalachia project, where the cow-calf portion of that research took place at the Virginia Tech Shenandoah Agriculture Research and Extension Center. There, 12 groups of 8 cow-calf pairs were rotationally stocked through 96 paddocks, with 8 paddocks per group of cows. The pastures were comprised predominantly of tall fescue with smaller proportions of orchard grass, Kentucky bluegrass, and white clover, and these were well established on fairly high fertility silt loam soils, and no fertilizer was added through the duration of the study. Of these 96 paddocks, 26 had their pasture herbage sampled once per month from April through October of 2008 through 2011, and those can be seen here in orange. The sampling consisted of harvesting a random swath of forage, selecting a sample, drying that, grinding it, extracting it, and analyzing it with ICP AES. That analysis resulted in the concentrations of 9 plant essential nutrients. We took those 9 nutrients and averaged the 4 years together, and I'll show you the results of this now. So, as you can see, on the x-axis runs from 4 through 10, so April through October, and the y-axis is the concentration of the nutrients in question. If you note the horizontal dotted line, that's the dietary requirement of a lactating beef cow. And as you can see, some of the nutrients like calcium and phosphorus consistently meet the requirements of a lactating beef cow, and some nutrients like zinc and copper and phosphorus for the most part fall below the requirements of a lactating beef cow, and some other nutrients are more marginal. Also, as you look at this, we see a little bit of a seasonal pattern, especially looking at nitrogen, sulfur, phosphorus, and potassium. We see a pattern of starting with high nutrient concentrations in the spring, those concentrations drop in the summer, and then rise again in the fall. So this is a little bit of an interesting pattern, but might make sense in terms of the context of what we know about pasture plant maturity. And so I had a question of what happens when we look at these years separately. How is there year-to-year variation in this pattern? And let's take sulfur as an example and look at that. So here we can see 4 years side by side, and if we look at 2008, 2010, and 2011, you can see that they continue to follow this trend of high concentrations in the spring, low concentrations in the summer, and high concentrations again in the fall. But what's really interesting is that 2009 doesn't follow that pattern. We see this consistent decline with lowest values occurring in October. And so, if you look at the average sulfur concentration for the average year, we have about 0.21% sulfur. And if you look at 2009, we only have about 0.16% sulfur. And so if you're a producer and thinking about optimizing your supplementation, you might expect that you would have high concentrations in the fall, but in the fall of 2009, for some reason, you didn't. And so I worked to try to explain what was going on in 2009, and to do that, built a statistical model. And so let's think about that now. For each of those harvests that we did, we went to the weather station at the site and collected data for air temperature, soil temperature, relative humidity, average precipitation, cumulative precipitation, and soil moisture. And so we'll ask the question, which of these would potentially impact that variation that we saw in 2009? And so then if you remember back to the slide where we saw all 9 nutrients next to each other, we saw that some of the nutrients were correlated to each other. They moved together throughout the growing season. We can take advantage of that and use a grouping technique called factor analysis to build a composite nutrient score, meaning that we don't have to model all these things separately. We can model them together and try to predict a composite score. And so the group that we're going to look at today is comprised of the variation in nitrogen, phosphorus, potassium, sulfur, and copper. We use an algorithm called all possible regressions to try to figure out which of those potential regressors will fit the best model. So the results of that analysis build a model that looked like this. So this is a little complicated, but let me see if I can just walk you through it. So we start with this nutrient score. It's a single value that's this composite of nitrogen, phosphorus, potassium, sulfur, and copper that we saw in the previous slide. And to predict that, we take the grand mean, and so that's just the average of all the values we have. Then we add the effect of the month we're trying to predict. And so if we're looking to predict June, we'll take the value for an average June. And if we're looking at August, we'll take the value for an average August. Then we add the effect of increasing soil moisture and subtract the effect of increasing relative humidity, plus a component of random error that we can't account for. As we go to analyze this model, we see that it has a statistically significant p-value and that it has an r-squared value of 0.84. That r-squared value of 0.84 indicates that we have captured 84% of the variability in that composite nutrient score with this model. So we're capturing the vast majority of the variability, indicating that this might be a good model to work with. So if this indicates that this is a good model, then we know what the question is, does it actually pick up that aberrant fall in 2009? So on the top of this slide, we see the actual nutrient score, and so this is based off our data. And then on the bottom of the slide, we see the predicted nutrient score based off our model. And if we look in the fall of 2009, based off this model, it does capture that aberration, these lower nutrient concentrations. So, as it turns out, in the fall of 2009, soil moisture levels were particularly low, while relative humidity levels were particularly high. And under those circumstances, we expect that the amount of water that's pulled from the soil through the plant into the atmosphere, the evapotranspiration, would be reduced. And laboratory studies have shown that as evapotranspiration is reduced, that the nutrient uptake of plants can also be reduced. And so, with this model, we can potentially predict the nutrient concentration of forages without having to sample them directly, potentially providing some good information to producers who are trying to understand the status of their pastures. And so for some conclusions, nutrient concentrations of pasture herbage nutrients vary throughout the growing season. Lowest concentrations occur in July and August. Soil and atmospheric conditions are related to seasonal variation in herbage nutrients, and soil moisture and humidity can be used to predict nitrogen, phosphorus, potassium, sulfur, and copper concentrations in tall fescue pasture herbage. And so finally, understanding the nature and causes of variation in pasture herbage mineral concentrations can improve livestock health, reduce production costs, and limit environmental losses. Thank you. Are there any questions? That's correct.
And then you use that model then to show that the way you show the model is correct was by predicting the data that you used to create the model.
Right. So the question is, I have just shown you an example of the model that we created, and then have sort of validated the model just by showing you that it predicted what it was based off of. And so that's not really a great validation method. I'm looking forward to the 2012 data, where I will have weather station data and be able to see if this model is actually valid. But just as a way of showing you that this model does capture that aberration in 2009, that's why I showed you what the prediction was of the model based off of the data that it came from. And so that's not necessarily a useful thing statistically, but I think in terms of explaining what I've been doing, that's useful. That's correct, or that's my intention. And then I will use it for validation. 2012 data we'll use for both validation, and then I'll add that into the model for the future. Yeah.
You mentioned that there are mixed pastures.
Mm-hmm.
Do you have any kind of estimate of annual composition? And if so, if not, how much do you think that affects the model?
The question was that these are mixed pastures with a couple different species in them, and how much do we think that the variation in species composition affected what's going on here. The vast majority of the species in these was tall fescue, and it doesn't appear that it changed with time particularly, at least year by year. So my sense is that that variation that we saw was smoothed out through the replication and sampling, and can't really tease out if it had a particular effect, but my sense is that it doesn't. Yes?
Can you say a little bit more about that group factor analysis? How do you decide which minerals go into that group?
So that's a little bit of a complicated statistical technique that is based off of the correlations, and so you between the nutrients, and that is something that is a factor analysis looks at the correlations and then tries to group based on correlations, and that is the biggest and best group that I could get out of these data, if that makes sense. That single score represents the greatest component of variability that could be expressed in these data. And so the next component that I would look at is one that looks at the variability of calcium and magnesium, because those trend together and trend very differently than what I've talked about here. And so that would be a next step for this, and to model those separately. Yes?
Do you guys take any soil samples to validate nutrients?
Did we take any soil samples to look at sort of the relationship? Yes, we took soil samples annually, and there's very little correlation between concentrations of soil nutrients and the concentrations in the pasture herbage. And my sense is that is because these are probably nitrogen-limited pastures, and we didn't soil test for nitrogen, and so long as you have one limiting factor, then things don't tend to correlate particularly well. Yes?
My other question is, how uniform were these pastures where you sample? Because you might have different growth stages that you might have a dilution effect in the forages. I think it becomes.
So the question is, how uniform were the pastures, and what were the growth stages at these samples? What was the growth stage of the pasture? Not uniform at all, heterogeneous. It was I don't have data about what the pasture looked like, or how, because this is a rotational grazing system, you might wonder how recently were these grazed, and that might give you some indication. Don't have that information. But there is enough, enough data here that we still find statistical differences that smooth over some of that some of the variation in the maturity of the plants at each sampling time. Thank you.